Hi, folks. Today we're here to talk about acids and bases. Give you a little bit of an introduction. Now, we see a little of imagery here associated with acids and bases. Some things that we think about. Kind of one of the famous things is acids like instantly melting the flesh from your bones, like we see in this little thing here. That's maybe exaggerated more than a little bit by Hollywood. The bottom line is both acids and bases can be dangerous if they're concentrated enough. Maybe not quite as much as Hollywood would have us believe, though. Okay, so the very first thing we should probably do is be able to recognize acids and bases when we see them. It's actually pretty darn important, as it turns out, in a unit about acids and bases. So this is the very, very first thing that you should make sure that you can do. Acids will always have a hydrogen, and it's usually going to be written first. That's a good way to recognize an acid. So those three things, hydrochloric, hydrofluoric, nitric acid. We'll be talking about organic chemistry. We'll be talking about organic acids. One thing that you're going to see to recognize them is they're going to have carbons, hydrogens. They're going to have two oxygens and a hydrogen. And in the organic acids, sometimes the hydrogen will be written at the end like this, but this double OH is going to be a giveaway that you're going to see in acid. Acids generally ionize, they break apart in solution. Notice they're covalent substances, but they do ionize in solution. So that's a bit of an exception of what we talked about before, what we talked about in the past in terms of ionization. Just a word of warning here, Lewis acids, which we're going to talk about later, are an exception to all of this stuff. Lewis acids are going to look a little bit different than this, so that's something you want to keep an eye out for. As far as bases go, most bases are going to contain a metal and the hydroxide ion, OH minus 1. And they're going to ionize to produce hydroxide ions in solution. So all of these are examples of bases. Potassium hydroxide, sodium hydroxide, barium hydroxide. All these ionize and break apart in solution. As we've talked about many times, they're ionically bonded. A term that you'll see in IB will use often, and I'll try to throw it in there as much as I can, is alkaline. Basically, something that's alkaline is a water-soluble base or something that's going to have hydroxide ions in solution. It's more or less a synonym with basic. I could say a solution's basic. I could say a solution's alkaline. It really means the same thing. A huge, huge exception to know is ammonia, NH3. It's also a base. Please be aware of it as a base. I really, really need you to be on board with that. Let's talk for a second about hydrogen ions. So if you think about it, if you think about it like a periodic table and look at it, hydrogen's element number 1, all it is, a hydrogen atom, a neutral hydrogen atom, is 1 electron and 1 proton. Doesn't have any neutrons, usually. There's some isotopes with neutrons, but usually it doesn't have any neutrons. So when we say proton, you take that hydrogen atom, it loses its 1 electron, all that's left is a proton. So a hydrogen ion, an H plus ion, and a proton, those things are basically synonymous. Another thing to sort of keep in mind is when we're talking about acids and bases, pretty much you're going to be talking about things that take place in an aqueous environment. So this is all taking place in water, all the stuff that we're talking about. So what happens is when you have a hydrogen ion, a proton, and there's all this water around, the hydrogen ions are really reactive. They're going to do something. And what they're going to do is they're going to stick themselves to the nearest water molecule. And what you have at that point is an H3O+. 3 hydrogens, protons are positive, so H2O becomes H3O+. And the bottom line is, when a chemist sees H plus aqueous and H plus in solution, they know in their minds that what we're really talking about, or what's actually present, is H3O plus, hydronium ions. You can essentially use them interchangeably. You'll see them both used in different contexts and in different times, but proton, hydrogen ion, hydronium ion, more or less, all different ways of talking about the exact same thing. So keep that in mind. So for a long time, people have known about these things that sort of reacted in a certain pattern. And people have sort of tried to investigate this and think about ways or how one could define what an acid or base is. You know, they knew they had these classes of chemicals that were doing this stuff, but how could they put a more kind of precise definition on it? And there's been a few of them throughout the years. But we're going to focus on two definitions, especially this one. This is the one that we're going to use 90% of the time, the Bronsted-Lowry definition. So basically, when we're talking about Bronsted-Lowry, we're talking about protons, we're talking about hydrogen ions. Acids are things that donate protons, hydrogen ions, to other things. Sorry about that. My dog almost knocked over the lamp. I don't know if you heard that. So acids are proton donors, bases are proton acceptors. So for instance, notice this reaction here. We got a nice little equilibrium reaction like we've been talking about. You've got HCl, which is an acid. So it can donate a proton to H2O. Proton goes from here to here, hydrogen. Notice the H2O becomes H3O plus, and then what you got left is a chloride ion. So HCl is the acid, it donates the proton. Water in this case is a proton acceptor, it's a base. You know, like it says here, bases are proton acceptors. So again, we have NH3, which I just mentioned is a base that you should be aware of. It's in a proton acceptor. It can take a proton, it can take a hydrogen from water. And that's exactly what it's showing happening here. The hydrogen goes from here to here. So in this case, water is an acid. Notice water is both an acid and a base in these two different equations. We're going to come back to that later, but water can be an acid or a base under this definition. So here's just another example, just trying to really show you the proton transfer that's going on here. So we've got a CH3 in solution. It approaches the water molecule. A hydrogen goes from the CH3 to the water. That makes HCl. Sorry, I might have said that wrong, but that makes HCl there, the acid. It's giving up a proton. Water's taking a proton. So acid base. Now, here's the thing though. We talked about equilibrium. We talked about the fact that reactions can reverse themselves. If this reaction goes backwards, then in that case, and the reaction that's going in this direction, the way my arrow is going right now, the hydrogen is going from the H3O plus, from the hydronium ion, back to the HCl, which gets us back to where we started. So in the reverse reaction, it's still an acid, it's still a proton donor, but they call it a conjugate acid. And if it's in the reverse reaction, but it's a base, they call it a conjugate base. And then we have these things called conjugate acid-base pairs. So notice the HCl is matched up with the Cl minus, and the base water here is matched up with the H3O plus conjugate acid. The definition is conjugate acid-base pairs are species that differ by exactly one proton. So notice HCl here is an acid. Its conjugate base is Cl minus. H2O here is a base in this reaction, and in the reverse reaction, its partner there is the H3O plus, which is the conjugate acid. Now, this is one of the core concepts of the Bronsted-Lowry thing, so we're going to spend some time definitely talking about this. I know it can be confusing at first. We'll go back to it in a minute, but I wanted to throw this definition here, amphiprotic. Amphiprotic are species that can accept or donate a proton depending on the circumstances. This means, I guess, is what's missing there. They can act as an acid or a base. As we just looked at a couple slides back. Water in some circumstances can accept a proton, making it a base. In other circumstances, it can donate a proton, making it an acid. So things that can either donate or accept a proton are amphiprotic. And there's a ton of things that are that way, as we'll kind of see. Okay, so let's look at this conjugate acid-base thing here again. So here we have a reaction, and it says identify the acid, the base, the conjugate acid, the conjugate base, and the conjugate acid-base pairs. All right, so basically In the forward reaction, that's always just our plain old acid and base. In our reverse reaction, those are the conjugate acids and the conjugate bases. In all cases, though, an acid is something that donates a proton and a base is something that accepts a proton. So if you look at the forward reaction, notice what happened to this. A hydrogen has gone from here to here because this thing lost a hydrogen and the H2O gained it. That makes that, which is acetic acid, the acid, and in this case, water is a base. If we think about the reaction reversing itself, the hydrogen would have to go from here to here. So this is the thing that's donating a hydrogen in the reverse reaction, but because it's in the reverse reaction, we call it the conjugate acid, and the other thing the conjugate base, and those are the pairs. Notice pairs always differ by exactly one hydrogen. This has one acidic hydrogen, as we call it. I know it has these other three, but this has one less hydrogen than it did before. This is H2O. H3O plus has one more hydrogen than it did before. Okay, here's another reaction. What I'd ask you to do is take a minute, just look it over, see if you can figure out what's the acid, what's the base, what's the conjugate acid, what's the conjugate base. So pause the video for a moment and see what you think there. So this is what that should look like. Proton, hydrogen goes from here to here in the forward reaction. That makes the bicarbonate ion here the acid and the hydroxide ion the base. If the reaction is going to reverse, though, a hydrogen has to go from here to here. That makes water a conjugate acid in this case, and the carbonate ion a conjugate base. And then you can see what's labeled as the pairs. Something that you might see is be give some chemical species and be asked to write the conjugate base of it, or sometimes the conjugate acid. But it's pretty easy. All we have to remember is they're always going to, conjugate acid-base pairs are going to differ by one hydrogen. So the conjugate base of something is going to have exactly one less hydrogen. And then we're going to think about what the charge would be, because protons are positive. So when you lose a proton, your charge becomes more negative. So the conjugate base that matches up with HCl would have one less proton, would be Cl minus. H2SO4, that's sulfuric acid. To write the conjugate base, we would write it with just one less hydrogen, and its charge would be -1. H3PO4, one less hydrogen, H2PO4, and the charge is -1. So just the conjugate base of something is going to have exactly one less hydrogen, and its charge would be 1 unit more negative than whatever you started off with. It's important, especially when we get into organic, we're going to study this a lot more, but ethanoic acid, it looks like this. There's 2 carbons, there's 3 hydrogens here, there's 2 oxygens, which there should be a subscript 2 there, that's missing, sorry about that. So the red ones here are the oxygen, and that's another hydrogen. This hydrogen corresponds to this one on this structure. So in more complex structures like this, yes, this ethanoic acid loses a hydrogen, but it doesn't lose any hydrogen. It loses one specific hydrogen. It loses this one that's attached to the oxygen. Basically, this one just isn't attached as strongly as these other hydrogens right here. So that's the one that it loses. And it's just something I want you to kind of keep in the back of your brain for now, something to be aware of. When we go back to organic, then it will hopefully make more sense. And people ask when they see this all the time, why doesn't it say? Let me pop those back up there. Why doesn't it say C2H4O2? Because they wrote it this way because they're trying to show you there is one acidic hydrogen. It's this one. That's why they don't mix it in with those. So it's the way this formula here is written. It's just a way to emphasize the acidic hydrogen. So I think it's about time to make an appearance from my friend Sam Jackson. Sometimes things need to get serious around here. Let's see. Which of those is not a base? not a base. Think about that for a few seconds. Actually, that's a trick question. They're all bases. Hopefully you notice all those. We've got our NH3 here. These got the OHs. Water can be a base. So Sam was trying to trick you there. Yes, they are, in fact, all bases. And I think before we go any further, before we go to this next part, kids, you really shouldn't drink. Because if you do, someone someday on the internet might videotape you or whatever you want to call it. And, you could have a picture like this of yourself post on the internet. So really, kids, be careful and say no to drugs and alcohol. All right. Lewis acids and bases. So there's a different definition of acids and bases. This guy named Lewis, and he's the same Lewis structure, same guy, Gilbert, the unfortunate first name of Gilbert. Old Gilbert Lewis came along and said, by the way, if your name's Gilbert, some future student watching this, I mean no offense. It's a cool name. Gotta cover my bases here. Lewis acids and bases, Gilbert said, we need to expand our thinking here a little bit. We need to sort of broaden our horizons when it comes to how we're defining acids or bases. Let's kind of encompass more things in our definitions of acids and bases. So he said, let's not define it by what protons are doing. Let's define it by what electrons are doing. So he said, I define a Lewis acid as an electron pair acceptor and a Lewis base as an electron pair donor. And at first glance, when you think about that, it seems like he's defining them opposite, like he's reversed what an acid or base is, but that's not true at all. All the things that we've already talked about that are acids, they're still Lewis acids. He's just thinking about it from a different point of view. And I'll show you some examples of what we're talking about here. And as I said, it's a broader definition. It's a bigger picture definition. So everything that we've mentioned so far that is a Lewis acid that is a Bronsted-Lowry acid would also fit as an acid under the Lewis definition. And everything we've talked about as a base would also fit as a base under the Lewis definition. So he's not completely changing the rules, he's just looking at it from a different point of view. Now that doesn't work the other way around. It's like saying all mammals are animals. You can say that. In other words, I can say all Bronsted-Lowry acids are also Lewis acids, but I cannot say it the other way around. I can't say all animals are mammals. That doesn't work because Lewis acids is a bigger, broader definition. Just a little schematic Venn diagram, I don't know, whatever you want to call it here. Lewis acid is the biggest picture one. All Bronsted-Lowry acids fit within that. And then Arrhenius acids, that's an even older definition that we didn't talk about. Don't worry about that so much. But that would even fit within Bronsted-Lowry. Now, despite all that, even though even though all Bronsted-Lowry acids are also Lewis acids, usually if someone says, hey, name a Lewis acid, what they really mean is name something that's a Lewis acid that doesn't fit under that Bronsted-Lowry definition. Technically they're not even using the word completely correctly when they do that, but in practice that's usually what they mean when someone says name a Lewis acid. They mean something that's a Lewis acid but doesn't fit under that Bronsted-Lowry definition. And we'll be looking at some examples here so you can see, but let's just get the kind of the definition stuff out of the way. So what you'll notice about Lewis acids is they're referred to as an electron poor thing. Sometimes they have less than an octet. We've talked in bonding about the octet rule. There are things that are exceptions to the octet rule, and they have less than an octet, like 6 electrons around them instead of 8. That would definitely make them a possibility to be a Lewis acid. Often they can be positive in charge. So those 3 things I've listed, BF3, Al3+, Cu2+, those are all examples of Lewis acids that are not Bronsted-Lowry acids. And I'll show you some diagrams and stuff to explain how how they can be Lewis acids. Lewis bases are, they're kind of the opposite. They're electron rich. You absolutely must have a lone pair of electrons to be a Lewis base because Lewis bases are electron pair donors. So you have to have that lone pair to donate. Often, but not always, you're going to find that Lewis bases are negative in charge. Now, IB in its infinite wisdom has given you very two similar terms and wanted you to know the difference between them. I thought they were basically synonyms, but apparently there is a really subtle difference between them. We already talked about amphiprotic, which is something that can act as an acid or a base by exchanging a proton. Amphipoteric is a bigger definition. It's something that can act as an acid or a base, not necessarily including proton transfer. So it broadens that a little bit. Again, I wouldn't worry about it a ton, but your syllabus does mention that you need to make a distinction between those terms. Probably doesn't need to be your highest priority, but it's something that they mention the syllabus, so I thought I'd put it in here. All right, so let's just really break this down and understand. If we look at what's going on here, okay, we do have an acid-base interaction here. We have a proton. So a proton, if you want to look at it, basically Lewis and Bronsted-Lowry are just looking at things from a different point of view. So looking at this interaction we see here from a Bronsted-Lowry point of view, we've got a proton, which is sort of donating itself to the water molecule. So got an acid here, a Bronsted-Lowry acid, a Bronsted-Lowry base, we make water. So a proton goes from here to here. But you would sort of look at it the other way around, because there's an electron pair here, and really what's happening is a new covalent bond is forming. So an electron pair is being donated by the base, the Lewis base or the Bronsted-Lowry base. It works in either definition. And the hydrogen ion here is accepting those electrons. So if you look at it from the point of view of the electrons, it's the base that is donating an electron pair, and it is in this case, the hydrogen ion that's accepting an electron pair. So in this situation, this is an example of where you've got, this is an acid under both definitions, this is a base under both definitions. Here's some more examples. BF3 that we saw earlier on the slide. Its Lewis structure looks like this. So now in this situation, there's no hydrogens here. There's no hydrogens anywhere. So this is why Lewis was like, we got to expand our minds here, folks. We got to encompass more interactions under the acid-base definition. If you look at the little boron here, it only has 6 electrons. It's sharing 6 electrons, so it would very much like 2 more electrons to get an octet. So my little fluoride ion, a little F minus, comes along. So it can donate these 2 electrons and form a new bond. So the BF3, or the boron in the BF3, has accepted a pair of electrons. That makes it a Lewis acid. And the fluoride ion is a Lewis base. So these are examples of things that are Lewis acids and bases, but they don't fit under the Bronsted-Lowry definition. So that's what it's saying about in this top reaction. In the bottom reaction, these are acids and bases under both definitions. If you want to look at it from the point of view of the proton here is donating itself, if you will, to the NH3. So proton donor, proton acceptor, Bronsted-Lowry acid, Bronsted-Lowry base, and we end up making NH4 plus over here. If you want to look at it like Gilbert does from the perspective of the electrons, we've got a pair of electrons here, so my Lewis base is donating a pair of electrons and the hydrogen ion is accepting them. Another common situation, another common thing that can act as a Lewis acid is positive metal ions, like Al3+, or really pretty much any positive metal ion in solution. What can and does happen is a water molecule can come along, which has a lone pair. It can donate a pair of electrons and form a dative covalent bond. That's the kind where both electrons come from one thing. Form a dative covalent bond with the, in this case, the aluminum ion, it actually ends up forming bonds with 6 of them. We'll talk more about these complex ions, we call them, but that's an example of how and why a Lewis acid or a metal ion can act as a Lewis acid. Okay, so there we have it. Hopefully that gives us a solid foundation on the various definitions associated with acids and bases. I know it can be confusing, particularly the Lewis acids. I know it can be confusing, but that's what we're going to use our class time for, to get you straightened out on that. So, as always, thanks very much for watching, and have a good